comes on?
Yep.
Good. I record the lectures. That was something we started doing a couple years ago at request of other people. Kind of wish I'd been doing this forever before the pandemic. But during the pandemic, I started recording because everything was asynchronous at first. And so I had lots of short little lecture videos and things. And then we went to live Zoom lectures that I recorded. But in the classroom, I've been recording a lot of my classes. I can't do all of them because it takes a long time. So on a daily basis, assuming everything goes well, I will upload this to YouTube and then eventually put on Canvas. It takes a while. It's a while, more than an hour to complete the process once I start. I have to transfer files to the computer, then merge the files, then upload. And it's a slow process. But I will hopefully have them up the same day. And the reason's real simple. You went to lecture. You understood everything, almost. And you go back and you rewatch something and go, oh, that's right, that's okay, now it makes more sense. Or you were sick and you stayed home, which I really would prefer you do if you're sick. And this is what we did in class today. It makes it a lot easier when you do that. Some of you take great notes. Others of you don't like taking notes at all, which is dangerous in a calculus class. But to be able to go back and watch a lecture and even rewatch a section of the lecture. Or maybe it's only 15 minutes of the lecture that you need, so you just go to that part. Okay, it's kind of nice. Another thing that YouTube does is automatically close captions everything. So you have the, right, and a lot of people complain. I talk fast, but not that fast, and I think I enunciate fairly well. And even though it's math, I've watched, and it's close to 100% in terms of the translation. You know, it's pretty good. I've heard horror stories, but I think it's actually really good. I think a lot of the horror stories came from people wearing masks while they were recording. So if you got to look at any of my videos from other classes, I always had my mask pulled down below my chin. I cheated a little bit because I wanted it to be clear. We're going to review a lot of algebra today. We're going to get right into the calculus. Next day is probably the most abstract lecture of the entire 3 semesters of the calculus sequence, but it's absolutely necessary to set the stage for everything else we're going to do. I will not make any assumptions about your background except that you're qualified to be here. If your algebra, trig, or geometry skills are weak, there are ways that you can get practice outside of class, but I will review everything we need to know when we're doing it. And I do this in all of my calculus classes, because if we're going to use a particular algebra thing, or a geometry thing, or a trig thing, rather than me just doing stuff and you saying, okay, I will trust him, because Mr. Brown's usually pretty honest. He doesn't lie to us that much. No, I want you to say, yeah, that makes perfect sense to me. I see exactly where things came from. I will never tell you a formula in this class. We will derive everything from scratch because you need to know where it came from, because when you get to your physics and other things, you're going to have to setting up problems doing things. You have to know how to start things from the beginning and then move on. Now, I want to take it to Canvas right off the bat. This is how I communicate with you the easiest way. How many of you saw the email that I sent with the syllabus? Raise your hand if you did. That's not bad, about maybe a third of you. A lot of folks aren't aware that you have a new email address. You have a district email address that was put in July, and a lot of students aren't aware. All communications by the district automatically are going to this new email address. So if you get to it, and my son is going to Mesa College, and he actually had to search through, I think it was the web portal, is that right? And he found it, and there were all sorts of emails on there. What you need to do is find your email address, and then you have the ability to have it automatically forwarded to the one you like to use. How many have done that, by the way? Was it pretty simple?
Yeah, you just go to Canvas and switch the email that you wanted to, and same thing for the portal.
Yeah, do it in the portal. Yeah, that's what you want to do, because most of you will forget to check the district email. You're checking your regular email on a regular basis, and you go, oh shoot, I've got 20 unread emails. So find it, switch it over, because all communications that I do with you, if I email the group, they're going to that address. Now, if you emailed me today from your other email address and I respond, it's going to that email address. That's not an issue. It's anything that I send to the class, I don't have access to your personal email, only your district email. That's why you want to have that one automatically forwarded. Unless you're really good and you check daily. I have to check multiple times a day. 100 emails for me is a slow day. Most days I'll get 200 emails. That's every single day. I've already checked my computer. I've gotten over 150 emails since this morning. A lot of them are people asking for ad codes. Others are just district stuff. So Canvas is a bulletin board. I put stuff on there for you to see. Canvas is not a method of communication. Do not email me through Canvas. I might get the email, I will never get any attachments. I won't get other stuff. And sometimes I only get a notification that somebody tried to email me. No, email me at my email address, the one that's on the syllabus and things like that, right? The sdccd.edu address, the one I get all sorts of stuff from. Anything you email, send it there, not through Canvas. Again, Canvas is how I give stuff to you guys. It's not how you send stuff back. Now, here's where everything is located, under modules. That's the only place you need to go. So right off the bat, you see all of this stuff. And there's all these pre-printed lecture notes. There are short videos that are just little helpful instructional videos that I made during the pandemic. I have every one of these lectures, I have a live version that's a Zoom lecture. That will be inferior to the live class, but these are things you could watch if you wanted to ahead of time. See, you can't rewatch today's class until maybe tonight. But you could watch the Zoom lecture of this class on my 3x4 whiteboard at home. And that, a lot of folks said, that really helps me get ready for the next class. And then I will have the live lectures posted here. And the first several quizzes are already up there right now. So let me go to the schedule. So here's how you open things. I go to the upper left, I click that, and now I go over here to this little arrow. And now what it'll do is it'll enlarge it on my screen, eventually. There we go. Now the nice thing about this, I can print this and check this out. I can make it bigger, or smaller. It's hard to read, so I'm gonna make it a little bigger. This is the schedule. You notice I don't have it by section numbers like a lot of your classes will. I have it by topic. The reason is, I truly could care less what calculus book somebody uses. I just need you to have a book so you have access to homework questions. To go through the class without a book and not practicing homework means it's very unlikely you will pass, and you certainly won't be prepared for next semester. You gotta be really good at this for the next 2 semesters. Practice is everything. So any book. The books that I suggested are the old Tan and the old Swakowski, not because they're well written, but because they are tremendous sources of homework questions. They have great practice problems. Not good explanations, but great practice problems. And they're also really, really, really cheap. Although you have to look a little harder to find them because they've been out of print for a while. Most people tell me they can easily acquire one for way under 30 bucks, and now you have a book for 3 semesters. Don't buy a new book, whatever you do. And the online resources, like the OpenStax and things like that, those are okay, but most people say they're not very good. The highest compliment I've ever heard was adequate. I've never heard anybody use the word good with any of the free online stuff. It will get you by, but if you are struggling and you need better, having a physical textbook often is really useful because you can practice. Now this is what we're going to do every day. You notice on Monday the 21st, it's no longer there. We had everything's been shifted one class. So what that did was, I shifted the first exam. Most of the classes I teach in a 32 meeting format. All Tuesday, Thursday classes meet 32 times. Monday, Wednesday classes generally always meet 31 times because they always have a holiday. So what I've done in the past is I often on Monday, Wednesday classes will throw in a Friday exam. I'll just move it. That way I get 1 extra class back because at the end of every semester, every class, I like to do 2 reviews before the final. I like people to have more time. Most of the classes you take between now and college graduation will not have any form of a review. I did graduate work in mathematics at UCSD, graduate work in statistics at San Diego State. Never had a review in any class I ever took. And we're talking like 60 classes, 70 classes. There's no review. You have the last class, you have the final. That's just how it works. We have review because I want that cushion of time so you're prepared. But to get that normally in a Monday, Wednesday, I would have a Friday exam. I didn't do that this semester, but now I'm doing it because we just lost a class. So the original exam 1 was supposed to be on this date, on Wednesday the 27th. What I've done is I've moved it, here's the schedule, see the little star, I've moved it to Friday the 29th, which is right here, which means that you can take the test any time between Wednesday and Friday, but I will select a room and actually have a room available on the Friday. Most people will say, no, I'll take it Friday. I want the most amount of time humanly possible to prepare. But you might say, yeah, can I take it on Thursday? I'll say, yeah. You might say, I want to take it Wednesday afternoon. Okay. If you're not going to take it Friday, we just work out the logistics. But you basically have like a 48-hour period. The reason is we need that class back. What a lot of folks are doing because of Monday's loss, they're just cramming more material in. I don't do that. That no work. We have a 2.5-hour class. I'm not going to cram another hour or two into each of the first few classes. You know, I'll lose half of you if I try that. Too much information. Plus, I have the whole course designed lecture by lecture already. So moving that first exam then means for the whole rest of the semester we're exactly on track, which is a nice thing. Okay? Now, this is what we're going to do every class. So what I want you to notice is here it says quiz 1. Each lecture has a quiz associated with it. We will practice problems in class. Hopefully you're practicing problems in a textbook that look very similar. You will have a quiz that looks like the same problems. But it's just a few questions. It's a quick way of me being able to tell you getting this stuff or you're not getting this stuff. You're supposed to get 100% on a quiz. You have a week. It's open book. We just did every single problem I asked you. I'm just giving you different numbers. Okay? The quizzes are due 2 lectures later. Okay? When you come to class, you'll just simply put the quiz on the table, so on. What if you're sick? Okay? What if something happens and you physically can't be here? The easiest thing to do is take a picture of your quiz, email it to me ahead of time. So what I recommend, there's something called the Fast Scanner app. This is wonderful. When we first went to the online asynchronous back in the spring of 2020, basically every instructor on campus required students to download this app. How many have used this app, by the way? How many have used Cam Scanner? It's the same. They're really no difference. For those of you who haven't done it, you download the app to your phone. There's a YouTube tutorial. I think it's 1 minute 40 seconds. It's designed for people like me who are just pathetic with their cell phones and technology and things like that. And you download it to your phone, put my email address in your phone, then you can't be here, you go like this. Click send. From beginning to end, it can't take 10 seconds. And this is insurance. If you are wondering, I may not make it to class today, then email me your quiz ahead of time. Then when you show up, hand me a hard copy. You emailed me a quiz. I teach early morning classes. What will happen with those classes generally is every single student, every single day will email me their quiz before they leave. And then they're all going to be there. But a lot of them have to travel. A lot of people are taking 15 South, by the way, in the morning. That's the worst commute. I've heard it's actually the worst commute in all of California. The 15 South, Escondido this way. It's gridlock every single day. And I had one student yesterday that said, that I joked, I said, how early did you leave? And they said, 5 for my 8 o'clock class. That's awful. Well, what if there's an accident on the freeway that day? You know, what? Things happen. I'm not just talking about you being sick. Things happen that might prevent you from getting here on time. Take a picture, send, then get here. I delete the email when I got the physical copy. But if you're not here, then when you get here, you hand me the physical copy, and that was insurance. And the process only takes seconds. Do not download the quiz to your computer. Because then when you send it, I will have to download it. And there's 2 things. I don't ever download anything, period, and you shouldn't either, because that's where all your viruses will come from. And secondly, my computer will delete anything that has to be downloaded anyway. I won't even know that there's an attachment. So I'll email you back and say, there's no attachment. And you go, well, I keep sending it. Oh, you're sending me a downloaded thing that I have to download. No, if you got a brand new car and you took a picture, are you going to download it? No, you're going to send me your picture. That's what you're doing with your quiz. You're sending me a picture. That's it. And the reason I like the Fast Scanner is because the majority of quizzes that you take a picture and send me will come in sideways. That's always the thing that makes me laugh. They'll come in sideways. But I can rotate it using that one. You have the ability to adjust the contrast. So you took a picture and it's way too light or it's way too dark. You can adjust the contrast on your phone. It's a very cool option. And then I have the ability to rotate it and even enlarge it. I can't do the contrast at my end. But it's a simple way to make sure if you did the work, you're getting credit. That's a huge thing for me. Okay? If you're absent, you still want to be able to turn stuff in. That's it. All right? Now, the first exam, you know, it's 3 lectures or 3 classes after the last material. So on this day here, September 20th, you see those 2 slashes right there. That indicates that's the last material that's going to be on the exam. Okay, then the next material is obviously the next exam. But also notice that quiz 8 is due before the final, or excuse me, before the exam. Every single lecture has a quiz. Every quiz you will have turned in before you're tested. So and also on that same day that I finish the material, I will post a practice test. I've actually posted the practice test, by the way. And I will also post a key. So you can practice and see how ready you are. Every question on the exam we did in class, you did on a quiz, you did on the practice test, you've got feedback, you've got keys. By the time you take the exam, hopefully you've done everything so many times that you already know. I just got done with a Calc 3 lecture, and most of the students have had me for the previous calculus classes. So I just said, tell me about the test, and they said we could have easily written it ourselves. I said, how close is the practice test to the test in the lab? They said, it's exactly the same, you just changed the numbers. But a lot of people don't take advantage of that, or they don't take the quizzes too seriously. Exams are scary. You're sitting down and taking a 2-hour exam, it's not open book, you gotta be able to do stuff. But hopefully you've practiced everything so many times, I don't wanna say second nature, but you can get through everything at that point. At the bottom here, these are all the important dates. This is the stuff that should go on your fridge. Now, in this course, I want to point out, go back to the syllabus now for a moment. There are 25 quizzes. The quizzes are not worth very much. The accumulation of quizzes are worth a lot. What I do in all of my classes is I make problems worth a lot. Oops. I have friends who teach, and I really respect them. They'll give this really complicated, maybe proof-oriented test, and every question will be worth 4 points. If you make a small error, you lost a point. Now think about that. I made a small error and I get 75% credit. There's nothing wrong with that. I'm making that same problem worth 50 points. And you made a small error, I took a point out. See the difference? I make problems worth a lot, so when you make a small error, I can make a small deduction and you're not losing huge amounts. Because does it matter how much anything's worth? No. In the end, it's all based on your percentage. So I make the exams 600 points. It doesn't matter if I made it 600 points or 60 points. It's still based on percentage. But by making problems worth a lot, then when you make small errors, or let's say you didn't do a whole lot well, but you did something well, I can still give you some credit. Maybe you did half the problem. Maybe you did 3/4 of the problem. But by making things worth a lot, you can get a lot more of the percentage of each problem that way. In other words, it benefits you. So in the end, and here's all the important legalistic stuff. Okay, the grading scheme. You have 3 600-point exams. You have 25 30-point quizzes. You get to drop an exam and 5 quizzes. You're not going to choose, it doesn't mean your lowest scores. Your best 20 quizzes are automatically going to replace your worst exam. Now, it doesn't mean you're going to have a bad exam, and nobody's going to have 25 great quizzes. But a lot of you are going to have 20 great quizzes. Okay? So your 5 lowest quizzes, off the table. So your best 20 quizzes, replace the exam. You get to drop an exam. You get to drop 750 points. That's a lot of points. Now, the final exam is worth 750 points. What if you don't have any lousy exams? You don't have any bad scores? Then you can drop your final. This is everybody's goal in all of my classes. Your goal is to not take the final. It says what you must achieve. You're dropping 750 points. That leaves 2,550 points left. Before the final exam, you will have attempted exactly 2,550 points. If you've already achieved 90% of that, you have an A without even having to take the final. The final will be your drop score if you choose. The final only counts if it exceeds your worst test and worst 5 quizzes. So everybody in this room's goal is to not take the final. This sounds silly, but because I teach sequentially, so it is not unusual by the time you get to differential equations. You might have been in my class in Calc 1, 2, 3, linear diffie, maybe discrete. I've had people that have, and I had one person have me 7 times because they had stats on me. I had people wish they wore t-shirts that said, I've never taken Mr. Brown's final, and they were very proud of that. And I just thought that was really weird. But I have students at the highest level every semester, but they've never taken a final. They made sure they earned an A in every class before they got there. And I'll explain when we're preparing for the final why I do that. Because most of you will find out it is rare that your final exam will actually affect your grade. That's actually really unusual.
You said that you have 2 days after the lecture for the quizzes, right?
No, each quiz is due 2 lectures later, not 2 days later.
Oh, okay. So the quiz 1 that's on Wednesday, 8:30, is that the?
That's today's lecture.
Okay, so today's okay.
Now I said 2, it's due 2 lectures later, because when there's an exam, let me go down a little ways. Here's exam 2, okay? Exam 2 is not a lecture. So the quizzes or the lectures right before there, exam 2 is in the way, so you actually have an additional class. Does that make sense? You have an additional class for those 2 because there was an exam, so it's always 2 lectures later. So when we have Thanksgiving week off, 2 lectures later now makes it 2+ weeks later. Everybody okay with that? A lot of folks say that they're always due 1 week later. Most of them are due a week later, but some are due longer. Nothing's due less than a week later, okay? And at the end of the course, your last 2 lectures, here's the last material, then you have a week off, then you have the last 2 lectures, then you have your exam. Oh my gosh, that 3rd exam is so far after your last, you have almost 3 weeks for that one to prepare. And then you'll have your review and your last 2 quizzes that were on those last 2 lectures. Every lecture of the semester will have a quiz, and almost every lecture will be on an exam. So again, you could write the tests for me in the end, because you know exactly what I'm going to ask. You just don't know what numbers I'm going to choose. And that's why in calculus, it's all based on practice and recognition. Once you recognize how to do a problem, you'll know what to do. But we learned so many things, and there are so many formulas. Now, I'm not going to talk about exams till we get closer to an exam. There's just too much going on. But that schedule is kind of a main thing. Okay, anybody have a logistical question? Again, this is important that you understand the structure and the format and all that kind of stuff.
So the quizzes are online, right?
All the quizzes are on Canvas.
Okay, and then we have to print them out, and that's the hard copy that we give to you?
You have 2 choices. Print the quiz, do your work on a separate piece of paper. I'm giving you the questions. I'm not giving you space to write. I'm just giving you the questions. Do your work. Please take as much room as you need. Don't try to squeeze everything into a corner and it can't be read. I don't need you to take multiple pieces of paper, but certainly most quizzes you can probably get by with 1 sheet of paper, both sides, but give me some space. I gotta read these. My eyes aren't that good. And then you just staple it to the cover sheet. Or you say, I don't want to print the quiz, then just do all the problems on a piece of paper and number them. There's 2 problems with that. I like it when you print the page. 2 reasons. One is, about half the people will print the sheet, half of them won't. That's okay. But the half that won't, at least half of them will make at least 1 error for miscopying a problem because they don't have the problem in front of them. They will simply do a different problem. How do I know? This is every single class I teach. The majority of errors come from the people who didn't print the quiz. They did the wrong problem. Secondly, one of the most effective ways to prepare for the exam is to retake your quizzes. Do you think you're going to remember your answers to quiz 1 a month from now? No, so they're brand new questions. But because I post a detailed key after each quiz, you can retake each quiz, grade yourself, and there's 2 things. If I got it right, do I still remember how to do it is the key. And if I missed it, have I got it right the next time when I tried it, walking into the exam? In other words, have I figured out that material? So you have a physical practice test, but really a secondary practice test by redoing your quizzes. Most of the students tell me that redoing the quizzes is maybe one of the most helpful things. When you're preparing for the final exam, retaking your old exams is one of the most effective ways. You see, it doesn't matter if you know it today if you forget it later. But if you don't know it today and you figured it out later, then you're good. Probably better to know it today and remember it later, right? That's our goal. But there's so much information that you will forget stuff. Again, more information in this course. Interesting thing is calculus is one of the slowest moving courses there is. But a calculus course has no review built in. Everything is new. That's why we will constantly review throughout the lecture and throughout the day. Okay? Questions are welcome at any time. So when we're doing a problem, close this off. We're doing something and you're not sure how I did that, that hand should go up. Say, can you explain where that came from, kind of thing. You know that if you have a question, it's probably safe to say half the people have the same question. You were just the smartest one to ask.
Do you have like sections or like little time slots where we like talk about things from the past lecture about the quiz or anything like that?
I have office hours. Yeah. In fact, for this class, I have office hours immediately following the class. One of the things on a daily basis, when the lecture is done, I'm going to concentrate on the video, but it's going to be 45 minutes minimum. So that's about how long my office hours are. I only have to be there. I'm not doing things. So I leave from here, I go directly to my office. That's the perfect time to follow me. I also have office hours early in the morning. Don't come to those. It's 3 hours before class. Why would you come to those? By the way, if you're already here, great. You do not have to make an appointment. You do not have to come only to one certain office hours. I put office hours next to every class I teach so that the people in that class, it's convenient. But anybody can go to any office hours. I have office hours Tuesday, Thursday. If you're on campus, swing by then. You can also email me. I answer emails all the time. I would prefer you ask me the math question in person. So you're holding your book and say, okay, I'm stuck on this problem. When you email me, could you imagine texting me a calculus question? Anybody ever do matrices? I had somebody try to type a linear algebra matrix. Yeah, you can't. No, so what a lot of folks do is they take a picture, they get a little sticky note with a little arrow, they'll take a picture of the problem and say, I'm stuck here. Or, am I on the right track? Or, I'm not sure what to do next. These are the questions people email me. Those are great questions. And I will explain the best I can, but it's really hard for me to type a calculus answer. Do you guys understand what I mean? That's why if you can come and ask me in person, it's so much easier to communicate. But what if it's Wednesday afternoon? What if it's Thursday, Friday, Saturday, Sunday? I don't want you to wait till Monday to ask the question. Ask me when you have it. I'll do my best to answer it. Now, I do get a lot of emails. And once the semester starts and people email me quizzes, I'm going to get 50 to 100 emails that are just the quizzes, not the 100 district emails I already get. So you emailed me and I haven't got back to you in a few hours. I could be ignoring you, but it's more than likely I'm in class, you emailed me, and by the time I get to my email, I've gotten another 50 to 100 emails, which means you're on page 2. And you have to go top down. So it might be hours before I see your email. So email me again. Just resend it. So I'm resending this because I haven't heard back from you. And then I'll answer it, and then later when I come across the other one, I do go through every email, and it takes a long time every day, but I do go through every one because some of them are junk. But if it's a student email, I try to answer it to the best of my ability. Sometimes they don't, you just say, Mr. Brown, I'm not going to be here. It doesn't require a response. That's not a big deal. But if it's something where you have a question, if I haven't got to you, send it again. Again, I'm not making excuses. If you saw my inbox, you would laugh if you looked at the times. It'll say 8 o'clock, 8:01, 8:01, 8:03, 8:04, 8:07, 8:09. Between 8 and 9, I got 75 emails today. That's just a normal day. So if you emailed me and I haven't looked at it, you're probably page 3 by now. So do that. We're going to start doing some calculus, but before we do some calculus, we're going to do some review because trig, algebra, geometry are all equally important in the setup. Everything I review is something you've probably seen at some point in your life, but it might not be right there. I am going to show you techniques algebraically that you have never seen. We're going to do a lot of stuff where we're going to maybe do really simple algebra, and you'll say, I have never seen it done that way. And I guarantee you, what I'm showing you will always be easier. Okay? I brag that I am the laziest person you could ever meet. Now, if you followed me around for the day, you might not come to that conclusion. Okay, if you saw a typical day of mine, I moved my office upstairs. We just did a big remodel, but I'd be in my office. The adjacent room is where the big screen TV is, so I got the hockey game on there while I'm working on a test and grading, and I'm making dinner, and I'm doing laundry upstairs, and I have a full gym in my garage that you guys would die over. It's better than most commercial gyms. And I'm working out, and I'm doing all those things simultaneously, and I'm doing all of them very well. I can multitask like you would not believe, and I'm doing all of these. 5-course dinner, laundry's the only one I really don't want to be doing, but I've got all this going on at once. Why? Because I'm lazy. See, I value my free time so much. Lazy translates to efficiency. The person who's lazy, by the way, if you're getting fired, that's not lazy. That's just dumb. You're not doing a good job. No, lazy means I'm going to get the job done, I'm going to get it done well, but I want to put in the least effort humanly possible. You understand? If this is the question and this is the answer, I'm going to show you how to do this. Most people in calculus do this. A lot of sideways motion, a lot of extraneous steps. Most algebra books will show you lots of steps, and I'll do the problem, I'll show you. Most every algebra problem you've ever run across in your life can be done in either 1 step or 2. And I'm not joking. I can't even think of an algebra problem that would require a 3rd step. But the textbooks, might have 20 steps involved, and I'll say, no, these are unnecessary. Doing a step in your head is still a step. We want to go from question to answer. We want it to be clear. We want to understand. And I will show you when you're efficient, it doesn't make it harder. It almost always makes it easier. And it's so much direct. Here's the idea. I need you to run over next door and grab something. So you go out the door, you go down the stairs, you go out the building, you go around the building, you go up here, you made it next door. You did exactly what I asked. That's what most people do in calculus. I'm going to show you how to go next door really quickly and efficiently. See my point? You can all get the answer eventually, but I don't want eventually, I want directly. Because if I asked you to explain it to someone else, would they understand? Would they be able to follow your reasoning? Maybe, maybe not. But you want it to be absolutely clear, everything you do, and you want it to be, this is the obvious step I want to do. Okay, so let's start with a little bit of algebra. One of the most important things that we deal with in this class is domain. Now, we are starting Calculus 1. Everything you've ever done in your life before this is technically pre-calculus. It was a development for calculus. Calculus 1 and 2 build off each other. It's literally one humongous continuous course. Calculus 1, 2, and 3 go together. Basically, it's Lord of the Rings. Anybody ever watch Lord of the Rings? The whole thing? Yeah, we have the extended version. It's great. They're like the extra 2 hours of stuff. Return of the King is 4 hours long, and so we always watch one disc at a time. But in Lord of the Rings, when the second movie starts, they don't spend an hour reviewing the first movie, do they? Isn't the first minute of the second movie would have been the last minute of the first movie? And same thing with the third. That's how calculus works. Your first day of Calc 2 is the next day of Calc 1. There is no going back and saying, here's what we did in Calc 1. It doesn't work that way. It is one humongous course that's split into thirds. You've had algebra courses where they kept reviewing. I'm not even going to ask about your pre-calc because you'll probably make me sad. But when I ask people pre-calc, oh yeah, pre-calc we graphed lines, we solved quadratics, but you did that in pre-algebra, elementary algebra, and intermediate algebra. Why would you do it in pre-calculus? My God, if you can't graph a line by elementary algebra, you're in trouble. Most people tell me what they did in pre-calculus, and it's exactly what they did in pre-elementary and intermediate. I needed you to be experts at conic sections, logarithms, exponential functions, fundamental theorem of algebra, which should take about a month of the course, but it might not have taken one day. Most of your pre-calculus, you did all the things you already knew. So therefore, the vast majority of all human beings will say the easiest math course they've ever had in their whole life, without any exception, is pre-calc, because it was the only course they ever had where they learned nothing new. And that's a problem. You should have learned a lot new. Sequences and series, did you spend a lot of time on those? Because you needed those for Calc 2, right? Partial fractions decomposition. Some of you, maybe, yeah, proof by induction. These are things that the state requires that your pre-calc course may not have done, because your instructor said, I want to keep it easy. I want everyone to like me. But they didn't prepare you for calculus if they did that. So we're going to review a few concepts. Calc 1 and 2 is the calculus of 2 dimensions. Calc 3 is Calc 1, more or less, in 3 dimensions. I just gave a Calc 3 lecture. So here's what I want you to all do. Close one eye. Now, you are going to master over the next few sections all the math of real numbers of this. Now open your eye. What just changed? Well, if something didn't change, you should not be driving a car. What just changed? Deb, you now can see 3D. You've never done and will not do any math until Calc 3 that's 3D. Now in Calc 3 you do all of this and you extend it to 3D because you've mastered the calculus of 2 dimensions. Then you extend it to 3D. Then when you go to your upper division classes, how many are engineer bound? Okay, one of your first upper division classes is going to be a course called complex analysis. It's the calculus of complex numbers, and everything gets weird. So you're going to then go to a different realm, but you're going to master calculus of real numbers. But before you do it, you have to be really good at algebra. What is domain? Well, if I have a function, if I said, I'm going to start with a simple function, y equals f of x. Most of Calc 1 we study functions. We don't study weird stuff. We stick with functions. You have a younger brother or sister who's just starting algebra, and today the instructor talked about domain, and what does that even mean? What kind of words would you use? What is the domain? There's another word that often goes with domain. A pair of words, domain and what?
Range.
So they're not the same thing, are they? What is the domain referring to?
All X values.
Okay, and what's the range referring to?
One.
So let's use a different word. The domain is everything that I can input. What's the range?
Output.
Everything that's output. They're not the same thing, are they? Quite different. Domain is literally the set of possible inputs. A lot of folks say it's the set of x's. Well, that's only if x is my independent variable. I could have f of t. You say, well, who does that? When you get to physics, 195, most people take that next semester. The horizontal axis is always t. You know what the vertical axis usually is? X. So that's why I said be careful. X and Y we do in algebra, and we do in calculus because we don't want to forget what it means, but it's not a rule. So rather than use a variable, it's the inputs, because I could easily use a different letter of the alphabet. In other words, the independent variable can be many, many, many things. The dependent variable depends on what you input. So we don't care about the range in this class. In general, we could care less about the range. In fact, if there's any complication of the function, I can't even tell you the range without a graph. I'd have to see a picture. And that should never be necessary to answer the question. But I can always tell you the domain of something. So if I have a function like this, let's keep it simple. I have f of x equals x squared. I have f of x equals 1 over x. I have f of x equals the square root of 9 minus x squared. The domain is what is possible to input. The first one is our favorite domain. What's the first one in words? All real numbers. Is that your favorite one? Yes. Anytime you can get that one, that's the one you want. That means there are no restrictions. Everything's good. So there's two ways to say that. I can literally say my domain is the set of real numbers, which we usually write as a script R. But most of the time we like to give intervals. So I'd say it's negative infinity to infinity. If I can give an interval, that's usually the best way of saying it. Now the second one, it's almost all reals. What do you think? All reals except 0?
Yes.
Everybody okay with that? How do you say that mathematically? There's a couple of ways of saying that. Let's start with the interval. Is it this? It's almost that. Remember, the open parenthesis means I'm not including it. So I've just given you the whole number line excluding the 0. That's fine. That's correct. But in words, when you said all reals except 0, that doesn't look like that. So there's another way mathematically that a lot of people like. I'm saying the real numbers and I'm removing. You can write a subtraction symbol, you can do a backslash. They both mean the same thing. It means I'm removing that. Why would I ever want to write it that way? I'm going to give you an evil one. If I use interval notation, I have to write 5 intervals union. Right? Because I have to have the 4. Would you say big yuck on that one? But in words, what would you say? Words, you'd say all reals except, that's a 4. Except -4, -1, 3, or 6. Do we all agree on that one? Do you want to write intervals for this one? Oh, heck no. Do you see why a lot of people like this notation better? It's just easier to say what I need to say. The most important question that we have for the whole semester is the one question that starts every problem. What is the domain? Every problem we do from a calculus sense, I'm not going to ask you the question. You're going to ask the question, what is the domain? Because when we solve the problem, and we're going to be doing things called optimization letter, which is considered the most important application. You know, what situation do I make the most amount of money? Or what situation is going to minimize the time I spend? It's called optimization. A lot of times we'll get an answer, and that answer is not actually possible. Because I somehow went outside of my domain, not realizing that I just gave you an impossible answer because it can't happen. It seemed like it could happen. We always identify the domain before we start the problem. That way when we're answering the question and I get an answer, go, no, that's outside the domain. Can't be. It's extraneous. It's not hard. It's just something that should be an automatic response. Now, This one. This is kind of interesting. Are there any restrictions on this one, or is it all real numbers? Now this is it. This is a trick question. If you were in an upper level class, there is no such thing as a restriction. In other words, complex numbers are totally okay. Every time in your entire life you ever answered the question, no solution. Have you ever answered that question in algebra? Yeah, that wasn't actually the answer. It was never the answer. Do you know what the answer actually was? There was no real solution. My solutions were imaginary complex, and I wasn't interested in those. I have a parabola that opens up above the x-axis. There are no x-intercepts because they would be imaginary numbers. That's totally okay. There are no real intercepts. But there's still a solution. My solution's just not real. So we just said no solution, but it turns out there might be complex solutions. And in the upper level classes, we consider those. How would you know if I'm considering those or not? Because Calc 1 and 2 is the calculus of real numbers and real numbers only. That means real inputs and real outputs. So if I gave you a large number here, wouldn't I get a negative under the root?
Mm-hmm.
And that value would be imaginary. My input was real, but my output was imaginary. So we're not considering that in this course. You will consider that in your upper level courses, but not Calc 1, 2, and 3. Okay? So this is what is called a real valued function. A real valued function will only accept real input and give real output back again. Okay, is that comforting? It's more of a, whew, okay, good. Because there will be scenarios where you allow for imaginary numbers and so on. This isn't one of them. So do I have a restriction here? Yeah, I don't want anything negative. So let's do some algebra off to the side. Tell me about 9 minus x squared. Needs to be what?
Greater than 0.
Does it need to be greater than 0?
Or, yeah, greater than
0 is okay, agreed?
Yeah.
0 is okay. Less than 0, not no work. Can I manipulate this? Throw that over, would I get x squared is less than or equal to 9? If x squared is less than or equal to 9, then what does that mean?
X is 3. You can take a root by
Can
side.
x be negative?
No.
Yeah.
Careful. Ooh. Boy, this is tricky. How about that? You like that?
That's about right.
That's the next thing I want to write. If x squared is less or equal to 9, then the absolute value of x is less or equal to 3, which means x is between what and what?
Negative 3 and 3.
Negative 3.
Everybody okay with that statement?
Mm-hmm.
That is the correct. So now how do I describe the domain of this? What symbol would I use? Good. Because we agreed that equal 0 is okay. So if x is equal to 3 or equal to negative 3, I'm good. And then everything between, I'm good. So this is how I would express the domain. Okay? So is this hard? Hopefully not, but it reminds us things that we need to know. Okay? Now I want to do a little bit of review of something else, because this is one of the things we're going to use quite often in this class, and it comes from what's called the fundamental theorem of algebra. There are many, many pieces of this that you would have been exposed to at different times, but you may not have realized what it was all called. Now, let me keep this really simple, because this is something we're going to use very, very often in this course. And certainly we're going to use this even today. All right? I have a polynomial function, and I'm going to put an n. That's just telling me it's going to be nth degree. So if I put P3, that means it's going to be third degree. P5, fifth degree, so on. An nth degree polynomial function, I'm going to write it like this. N has to be a positive integer, or this would not be a polynomial. There's no square roots, no weirdnesses. So if n was 5, then this is fifth degree. If n is 10, it's 10th degree. If n is 2, it's second degree. This is an nth degree polynomial function. Okay, great. We've dealt with these. What if I needed to factor this? Yikes. If it's quadratic, I'm good. If it's cubic, Fourth degree, change major, right? Kind of tough. If I factor out the AN, absolutely this can be factored into n factors. Absolutely. You notice I factored out the lead coefficient. So if I multiply all this back out again, I'll get the original. The r's are called the roots or the zeros of the polynomial. Hopefully you've heard those terms before. I like using the term root. The zero of a polynomial isn't the number 0. It's the value that would cause the polynomial to equal 0 when evaluated there. So if I said, keep this simple, if I said what's Pn of R2? 0. Every one of these values, if I plug it in here, will give me 0. Because it would make one of those factors 0. Every nth degree polynomial has exactly n roots. Some of the roots can be repeated, and some of the roots can be complex. Does that sound familiar? And the complex roots generally come in conjugate pairs. Is that an absolute rule? It's an absolute rule if the coefficients, the a's are coefficients. If those are real numbers, then complex numbers must come in conjugate pairs. Is it possible I could have one of these, those aren't real numbers? Yeah, but that's way, way later in life. Right now, all real numbers, coefficients. So that means that every polynomial, absolutely every polynomial can be factored. I'll have some fun with it. You're in baby algebra. The first one is a difference of squares. Agreed? We know this. We have no doubt. So if I set it equal to 0, you also know you have two solutions, plus or minus 3. What about the second one? If you're in baby algebra, you're told to write the word, starts with a P, rhymes with rhymes with rhyme. What are you told to write in algebra? Prime. Really? I'm pretty sure I can factor this and it has two real roots, plus or minus root 8. Do you all agree with that? You were lied to in algebra. It's not prime. That's a dumb answer. Because in algebra, they say, no, you can only factor it if it has integers in the factorization. You can factor anything. Well, what about the last one? It has two imaginary roots, and I just factored it. Absolutely everything can be factored. There's no such thing as prime. There are factorizations that do not involve integers or rational numbers. That is true. So in algebra, we say if the factorization does not involve rational numbers, that's what we'll call prime. But the problem is if I set this equal to 0 and said solve, these are easy. This one is imaginary, but I factored all of them. Everything can be factored, but not everything has real roots. You with me on that? Okay, so most of the time we are concerned. Now here's the other thing. Here's one of the main things, and this is part of the fundamental theorem. I haven't factored anything yet. Now, going back to pre-calculus, I have to factor this. So you use synthetic division, you remember, to try to find roots? You looked at every possible integer factor of this one, you looked at every possible integer factor of this one, and then you took every possible quotient. Remember that? It was called the rational root theorem. And then you used synthetic division and you tried numbers until you got something to work. So here's the rule. If Pn of C, for some number C equals 0, then x minus C is a factor. This is the most important fact that we're going to use in this class. And the funny thing is, I used to teach Math 46. We learned this in 46. It's called the remainder theorem. If I have a number that when inserted gives me 0, it means that x minus that number has to be a factor, because remember, it comes back to this. So what you did in pre-calc probably was you tried a little bit of trial and error. You found possible roots, you put it in, use synthetic division. If you got 0 as your remainder, life was good. Or you just plugged it in and got 0. Life was good. And then you knew what your one less, and you could whittle it down, eventually. Well, in calculus, we do this kind of stuff all the time. So let me give you a really simple example. I want you to consider the following problem, and we will come back to this one. Let me double check. Hold on a second. No, that's right. Hold on. Plus 14. Yeah. I want to know what is the domain of this function, and I would like to know if this function can be reduced. For a quotient to be simplified, it means numerator and denominator must have a common factor. That's the only way you can reduce a quotient. Okay? Yikes. So that kind of means I have to factor everything, doesn't it? Ugh. Well, the bottom's pretty easy. Do you agree that the bottom's pretty easy? How does the bottom factor?
X plus 2, x minus 2.
Okay. Now, if my numerator has a factor of x plus 2, then I can factor and cancel. Agreed? If my numerator has a factor of x minus 2, then I can factor and cancel. And if my numerator has neither factor, then I'm done, aren't I? There's nothing to do. Agreed? Those are my options. Well, how am I going to determine if the numerator has those factors? Just plug the number into your numerator. This is the easy way. So sometimes the process isn't hard. Let's put a -2 into the numerator to see if x plus 2 is a factor. Okay? Let's put a -2 up here. And what would this be? It would be -8.
Plus 14.
So that would be 4 times -7, so minus 28. -2, so that'd be -6 plus 14. Is that 0? No. So is x plus 2 a factor of the numerator? No. That's it. We're done with that. Now let's try +2. If I put a 2 in here, what do I get? I get 8 minus 28 plus 6 plus 14. What do you think? Is that 0? That means x minus 2 is a factor. I'm going to go out on a limb here. I have absolute certainty my numerator looks like this. I just don't know what the rest of it is. You with me? Absolute certainty. How do I figure out what the rest of it is? Well, the simplest way, it's not the only way, but probably the simplest way is to use synthetic division. Long or synthetic, but synthetic would be easier. I'm trying to factor my numerator, and I already know, right, that 2 is a root. So you guys remember how to do that? You take all the coefficients and write them in descending order. And what goes here? The 2. I'm checking 2, not -2. I'm checking the root. So this is a quick reminder of, we do use synthetic division often. Back in baby algebra, you all learned long and synthetic division, maybe even in the same class, because they're usually right there in every textbook. Everybody hated long division. Everybody loves synthetic. And then you get to calculus, everybody can do long division, everyone's forgotten synthetic. Why is that? Because synthetic has restrictions that long doesn't. See, for synthetic division, my denominator has to be linear, the leading coefficient has to be a 1, and they have to be the same variable. None of those are restrictions in long, but you find out you'll use synthetic far more often than long division, and it's so much faster. So, what do? Bring down the 1, and then as I learned from a student many years ago, you mama the problem. Anybody know what mama stands for? Multiply, add, multiply, add. In this case, you're going to mama. Multiply, add. Multiply, add. Multiply, add. Right, crowd goes wild, confetti everywhere, right? People dancing in the streets. Why do I love the 0? Because that's the remainder. In synthetic division, that's the remainder. That means it was a factor. If that wasn't 0, I'm in big trouble, aren't I? So how do I interpret what I have left? Constant, linear, quadratic. So how do I determine what's left? It's going to be x squared minus 5x minus 7. If I have any doubt whatsoever that this is correct, what should I be doing about right now? Multiply it out, yeah. I taught remedial algebra, and you're multiplying out polynomials, and that was kind of messy, but we got good at it. And it's like if I said, here's a whole bunch of numbers, add them all up. There's no check, is there? I got to add them all up. I'm simplifying. I'm giving you a quadratic, and I ask you to factor it, and then you factor it. The one question you don't ask is, did I factor it correctly? I'd say, multiply it back out again. If you get the original thing, then you did it right. I mean, you never ask, did I factor it correctly? Just multiply it back out. If you doubt whether you factored it correctly, multiply it back out. And now I can finally say what? The reduced version is this. Do you believe that this will be easier to work with? Now, can I keep going? What if I use synthetic division on this? I want to do this because this is something we will do in this course. This absolutely is equal to this. I love that. But synthetic division on this, what's my root now? Negative 2. It's what makes this 0. And what are the numbers? 1, negative 5, negative 7. Now we're going to get mama it. Negative 2, negative 7. 14, positive 7. That's not a 0. We weren't expecting a 0. I'll bring this up here now. So I apologize. I see the back row people when I see you moving sideways. There's a line in the sand. I think it's about here. Am I right? That the people in the back, you can't see below this line. So I try to keep everything up for the folks in the back. So what does this now equal? X minus 7 plus 7 over x plus 2. Everything we did are skills that we want to sharpen because they're skills from earlier classes that we may not have used in a while. Now, I said I wanted the domain of this also. Is the domain of this all real numbers? It's not all real numbers. What is excluded?
Negative numbers? Actually, negative.
Well, we said the original quotient reduced all the way down to this. I mean, look at that term. Are there restrictions here?
Negative 2.
So if I said, what's the domain? You'd say it's all reals except
Negative 2.
negative 2. Right? Be very, very careful.
Check it out. And 2.
Can x be 2? No, because 2 would have made my denominator 0. But I don't see 2 over there. This is the coolest type of factor there is. This is the one we're going to spend more time on than anything else. I just removed it from the problem. It is no longer there. We have a very clever name for this. It is called a removable discontinuity. I factored and canceled something. But x can't be 2. If you put a 2 in here, won't you get 0 on top and on bottom? And that's not a number. That's called an indeterminate form. And we spend a lot of time in calculus analyzing those kinds of things. So x can't be negative 2 or 2. Just because I eliminated it from the answer doesn't mean it's fair game. So we're going to look at a little bit of this, again, right after the break. Some of these things I'm going to come back to. So let me go back. This is a remedial algebra question now that I'm going to ask. I've got f of x. We're going to come back and look at this in just a few minutes. It's x squared minus 1 over x minus 1. And I want to draw the graph of this. Because I want to study the graph. Obviously, there's weird stuff going on. Do you agree? Clearly, x cannot be 1. What if I put a 1 in my numerator?
0.
I'll get a 0.
It's 0 is 0.
So that means that x minus 1 has to also be a factor of the numerator, doesn't it? If I'm getting 0 over 0, then I have something that's a factor of both because it was a root of both. Huh. Do you agree that that's what the numerator factors as? So what does this quantity equal? It's just x plus 1. Hold the phone. My domain has a restriction here. It's the illusion here that it doesn't have a restriction. Is there a restriction? Yeah, we're going to go back to remedial algebra. If you were in a remedial algebra class, I call it the disclaimer at this point. This is absolutely equal to this as long as x is not equal to 1. You have to write that in there because that's a domain restriction. X cannot be 1. Now, I said I wanted to draw the graph of this thing. Well, the graph of x, the graph of y equal x plus 1 is pretty darn easy. This is the line y equal x plus 1. But my original function is not exactly the same. Why? Because x can't be 1. How many remember doing something like this ever? What did I do? I just wrote the graph y equals x plus 1, but I removed a point. Now, you can't see a point. If I do this on Desmos, it's going to look like the line. You're not going to see anything removed because a point doesn't take up any space. So the way we represent this, and by the way, where would that point be? Wouldn't that be at 1, 2? So this is this line with this point removed. Now, hopefully you all did something like this in the past, so this isn't completely uncharted territory. That's kind of cool, isn't it? If I do this on any technology, I'm not going to see the hole, because the hole is a point removed. That point is called a removable discontinuity. I removed it from the graph, but I only removed the 1 point. Kind of neat, but you with me on that? Everybody okay? So if I want to do the graph, technology will let me down on this one. Technology has certain restrictions, and we're going to do a lot of technology. Here's one of the points I want to make. We will do a lot of things with graphing in this class. After, not before. A lot of folks will try to do a graph and then answer the question based on a picture. That doesn't work. It doesn't work. No, we're always going to do the calculus, and then afterwards we're going to draw a picture to explain the calculus we just did. And the picture will then kind of justify what we said. This picture justifies that over there. But if I started with the graph, I might not have been able to finish this problem. Could you imagine trying to plot points here? I make a big table of x's and y's and not realizing I'm just graphing a line in the end. That'd be kind of a silly thing. But I do the graph after I do the problem to help me understand the problem. Never the other way around. Remember, you're going to do calculus in 3 dimensions at some point. There's no graph. There's never going to be a picture anymore because you can't do that in 3D. All right? Now, the last piece of review today, this was reviewing the fundamental theorem of algebra, which in no other, if you don't think of it any other way, if I have a polynomial and I have a quotient of polynomials, any number that makes the numerator and denominator 0 simultaneously, then x minus that number must be a factor simultaneously, therefore I can cancel. And that's a powerful tool that we're going to use often in this course. Okay? There's a name for this, and I need you to know it. I use vocab all the time. I'm using math vocab because I want you to build your math vocabulary. And we're all guilty of this. You're understanding everything goes on, and I use a word you've never heard. And everybody just saying, yep, and in your mind, I have no idea what he said. I use one word you don't know. What happens to the rest of the class? It's gone, isn't it? I use one word you don't understand, you can't follow the rest of the class because you don't know how it's going to relate. If there's vocabulary you don't understand, you have to ask, because I'm going to constantly be introducing vocabulary that's very specific to what we're doing. This is called a rational function. We're going to do these more than most things. What is a rational number? What do you think?
Remember that can be written as a fraction.
Perfect. Any number, like 3/4. Would an integer be a rational number? 7?
Yes.
Because I could write it as 7 over 1. So any number that can be written as a fraction, and by the way, the definition of a fraction is any number that's a quotient of integers. X over y is a quotient. X over y is not a fraction. Root 2 over pi is a quotient. It's not a fraction. 1/2 is a fraction. So we have to make sure we understand. A rational number is any number that can be written as a fraction, quotient of integers. A rational function is any function that is a quotient of polynomials. Because a polynomial can only have integer exponents. So rational function, quotient of polynomials. Rational number, quotient of integers. Rational functions we're going to deal with all throughout the 3 semesters of calculus and beyond. That's a common term I want you to be familiar with. So when we use it, you don't go, oh God, he used it again, I don't remember. I have a funny story I tell every class. And, a few years back, I did my mathematics at UCSD, and then I waited several years, and I did statistics at San Diego State, the master's programs. And when I went to state, I was teaching here full time. So I'd take 1 class in the evening, some semesters 2, and then I did what's called a sabbatical, which is like the greatest thing ever invented. That's where they paid me my full-time salary to move to the top of the pay scale. They paid me my full-time salary so they could pay me more when I was done. You gotta love something like that. So my last semester at State, I was a full-time student, but everybody knew me there. They knew I was an instructor. I actually led 2 hiring committees when I wasn't even a student there for statistics professors. And on more than one occasion, instructors would stop and ask me how they got stuck on the problem because they were using high-level calculus, which the other students didn't really like that, when a student was taking over, but it worked well. So one of the classes from the late Dr. Liu, who I loved, I had many classes with him, one of the most published statisticians in American history. And he's teaching a class, it's a really gnarly class. And everybody in the class is a PhD in something, in a lot of health sciences and different things. And he kept talking about this function, and we need a parsimonious variable. And he kept saying, we need a parsimonious variable. All I could think of was that creepy orange fruit that my grandpa used to bring over in a little, persimmon. Parsimonious, I have no idea what he's saying. And like this whole lecture, I have no idea what's going on. I've never heard a human being use the word parsimonious in a sentence. I still haven't, by the way. So I go home and I look it up on the internet. Do you know what parsimonious means? Anyone guess? Stingy. So I go back to the lecture, I took great notes. In the situation, it was very complicated. Stingy means you don't give up much. You keep it in. We needed a variable that doesn't give out a lot of information, therefore the least information would be required to use this variable on and on. Oh, everything made perfect sense. Next lecture, 2-day-a-week class. He's going on and on and on and on. He gets to the point, what do we need now? And I raise my hand. At this point, we need a parsimonious variable so we can complete this process, blah, 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 blah. There's maybe 15 people in the class. It got absolutely silent. And I could actually hear, he said the word. Class is over, the instructor leaves. Literally the entire class, they run, they block the door. Could you explain to us what that means? Every person in the class, when he was talking in the first class, yep, and I'm sitting there going, I have no idea what he's talking about. So I went and looked it up. I understood everything from that whole week. These people, the whole week was gone. They were asking me to explain what just happened in the previous 2 classes. They were all faking it. We are all guilty of doing that when we have no idea what's going on. I have no idea what he's talking about. No, what are you talking about? Please ask if you are not sure, because you're going to lose what follows. I'm not going to ever use obscure vocabulary. I'm going to use common vocabulary, but it might be new. When we get to linear algebra, oh my gosh, you learn so much vocabulary that you never heard all in a short period of time, because it's for that next section of things. If there's one word you don't understand, everything can go astray. Now, I'm going to do a little bit of trig review right now. We'll take a break, and then we'll come back and we'll actually physically start the calculus. I'm going to show you all of the trig you've ever learned in your entire life that you need. You ready for that? It's not going to take that long. All the trig you've ever learned in your life that you absolutely need to do calculus. Okay? And hopefully everything I do you've seen. I know. I can draw perfect circles. Can't draw line segments. I have a perfectly constructed rotator cuff. People are always amazed at my circles. You should see my spheres. But if I try to draw a right triangle, people go, that's not even a right angle. It's kind of sad and pathetic. This is called the unit circle. We're not going to do anything with complex numbers. In upper level class, I'll do all this again, and we'll do complex numbers, and it gets really crazy and really hairy. This isn't. Okay? I'm going to give you a symbol you're not familiar with. The cosine of theta is defined to be x. 3 bars means is defined to be. It is not equals. Equals is a result. I would have to show it. I'd have to prove it. This is a definition. When you go to the dictionary and you look up a word, you don't say, well, why is that the definition? You go with it. What's your area code? You're before.
What was that?
619-858, what's your area code?
619.
Why is it 619? Because that's what the phone company gave you. What month were you born?
August.
Why August? Can I ask why to these questions? No. That's the definition of your birthday in a sense. I can't ask why, that's what it is. You cannot ask why on a definition, that's what it is. You can always ask why on a result. This is the definition of the cosine function. It is the x-coordinate on the unit circle, period. There's no other way to define this. Sine of theta is defined to be what?
Or
The tangent of theta is defined to be y over x, the slope of that line segment. Oh, by the way, isn't y over x sine over cosine? That's an equals. As a result of the definition of the tangent function, as a result, it is also equal to sine over cosine. If you were told that's the definition of tangent, then you were lied to. That is not the definition. The definition is y over x. The definition of tangent is actually the slope of the line here. That's the definition. Tangent is defined to be a slope. It's a ratio. Oh. So see why that's an equals now? Now, what about the other functions? The secant of theta is defined to be what? 1 over x, which as a result just happens to be 1 over cosine. The functions are not defined in terms of each other, they're defined in terms of the x's and the y's. The cosecant, 1 over y, which just so happens to be 1 over the sine. And the cotangent is y over x, oh, which just so happens to be 1 over the tangent, which just so happens to be cosine over sine. Those are results.
You're saying y over x.
I'm sorry, say it a little louder.
You were saying y over x, and you're saying you meant x over y.
Oh, I got, thank you. On cotangent, it's x over y. Thank you. Was it do as I do, not as I say? I don't know, something like that. Those are the definitions. We got to know those. That's not an area where we can struggle because we're going to, bad things can happen if we get those wrong. All right, let me finish this picture here. Isn't that a right angle? And that's x and that's y? Now, I taught high school geometry for a number of years, and it's really cool to prove the Pythagorean theorem using nothing more than similar triangles. I'm not going to prove the Pythagorean theorem. I'm going to give you credit that you remember your Pythagorean theorem. Pythagorean theorem in that picture would be what? Anybody? It'd be x squared plus
that's what equals 1.
equals 1 squared. Do you all agree that that's absolute from that picture? Okay. We're good? But if x is the cosine of theta, then that means this is the square of the cosine of theta plus the square of the sine of theta equals 1. Huh. Now, what I said was true, but from a notation standpoint, most of us hate writing the parentheses with trig functions. So we have a nice little, not a trick, a tool. When I'm doing trig functions that are raised to positive integer powers, not fractional exponents, not negative exponents. If I have a trig function that is raised to a positive integer power, I can write it like that, can't I? And most of us would do that just because it's less writing. That's all. Right? It's the same thing, it's just less writing. It is always correct to put parentheses around the outside. But I'd rather put, tell me. What do you think? What's wrong with that?
The theta squared, not
I'm squaring the theta, not the function. There's no possible way this can be interpreted as squaring the cosine. But you have it here. I have it outside the parentheses here. Right? Oh, never do that. If I do that on my calculator, right, I'm going to get something really wacky. So this is called a Pythagorean identity. Are there any more of these? Yeah, let's go back to this statement here. Let's multiply through by, how about 1 over x squared? Then I would get 1 plus y squared over x squared equals 1 over x squared. Okay, cool. But that would be 1 plus, how about if I write it this way? Which if I now go to here and here, this is 1 plus what?
Tangent squared.
The square of the tangent function equals, ooh, that's kind of cool. Is there one more?
Yeah.
Yeah, I do the same thing, but multiply through by 1 over y squared. So go back to that statement. If I have x squared over y squared plus y squared over y squared equals 1 over y squared, then that's x over y quantity squared plus 1, equals 1 over y quantity squared. But that would be the square of the cotangent plus 1. And thus we have the 3 Pythagorean identities. These are very useful, not because you're going to have a lot of cosquared plus sine squareds that you're going to be adding. No, it's actually very useful because I can substitute. You see, if I have a cosine squared, I could replace it with 1 minus sine squared. Right? I could do things like that. And it's going to be common that we manipulate these. So is this all of the things you need to do? Nope. Nope, there's one more set. These are all critical, but these are all fairly simple, and these are things that we are probably somewhat familiar with. Now, I'm not going to derive the next one. It takes a little too long. You hopefully derived this in a pre-calculus class. It's the cosine alpha plus or minus beta and the sine alpha plus or minus beta. I like using alpha and beta. Some books use U and V's. You know, doesn't matter what symbols you use. These are sometimes called the sum and difference formulas. Now, these are not formulas you use a lot. We will use these a little bit in this class, mostly to derive bigger things, but they give us some other formulas. Anybody remember this one?
Cos alpha plus beta
So it's cos,
minus plus.
I'll put sine, and it switches, good. Now, most people just go cos, sine, and then switch. Okay, what's the other one? This is sine cos, and I keep the same SIG in it. Okay, now, do you use these a lot? Not a lot. They're used sparingly, but they allow us to derive a way, way, way bigger formula, the double angle identities. The double angle identities are very important. The double angle formula for cosine is arguably the most used trig identity there is, significantly more than even the Pythagorean identities. That sounds odd. We use it in so many different capacities. The double angle formula for cosine. Well, how is this going to help? If I said, what is the cosine of 2 theta, could I consider that as the cosine of theta plus theta? Now go back to here and replace my alpha and beta with theta. You see what? Now what would that give me? I'm going to use that formula over there. I'm going to replace alpha with theta, and I'm going to replace beta with theta. And then that would give me cos, like you said before, sine, and this would be minus. Or I could write it as cos squared minus sine squared. This is called the double angle formula. But there are other versions of this. Because what if within the problem, sometimes you're trying to solve an equation and you have sines and cosines at the same time. That's really hard. I needed all sines or all cosines. What if I replaced sine squared, I've erased it. What if I replace sine squared with 1 minus cos squared? Is that legal? Then this would become 2 cos squared theta minus 1. what if I replace cos squared with 1 minus sine squared? Then this would become 1 minus 2 sine squared theta. If you look on the covers of every calculus book ever written, they will have all of these. They'll always put all three of these together because they're all the same formula. It's just which one do you feel comfortable with. This is the double angle formula. It said it's the single most common one because it's also used in another capacity. I have a problem where I have an angle, could be x, and then somewhere else in the problem I have an angle of 2x. When you're doing the math, you have to have the same argument all the way through. The argument cannot change. Right? I can't be working with the sine of x and the sine of 2x in the same problem at the same time. It won't work. So it's harder to go from x to 2x. It's way easier to go from 2x to x. So this allows me to do this. But there's another thing. The calculus of sine squared and cos squared. We haven't done any calculus on it yet. But the calculus of sine squared and cos squared can actually be really difficult. There's a lot of things I can't do with the square of the function. So what if I started with cos squared theta? Could I simplify that in terms of the other part? Yeah. Take this and take this. If I isolate the cos squared, we'll add 1 to both sides. And then take half of both sides. What if I started with a sine squared equals? Well, let's see, if I throw that over and I throw that over and I take half, it's going to look like this. I'm just putting those together. And you notice really quickly, if you add these two together, it will add up to 1, just like these will. This is the double angle formula. What do most textbooks call these? Anybody know? The half angle formulas. It's the same formula. Most textbooks will refer to these as the half angle formula, and that's the double. It's the same formula. I just rewrote it. This is why I said the double angle formula for cosine is by far the most commonly used formula, because you see all the different facets. Every one of these we will use in this class multiple times. The double angle formula for sine, far more obscure. Far more obscure. We'll do the same thing. Sine theta plus theta. So that would be sine theta cos theta plus sine theta cos theta. Well, that's kind of boring. That's just 2 sine theta cos theta. That one is useful, but it's used a lot less than the cosine. Okay. Now what? That's it. This is what you have to know for calculus. Is it, what about all the graphing we did? No, it's useful to be able to know what a sine wave looks like. How many sine waves are you going to graph between now and the day you die? Probably none. So why did you have to do it? Why did you have to do the phase shifts and the amplitude changes and all that? Because you're going to be in a physics class looking at an oscilloscope. You know what an oscilloscope is? It's a little machine that generates sine waves and things. You're going to be looking at an oscilloscope. You're on the job. You're looking at an oscilloscope, and you know what you have to be able to do? Determine the phase shift, the amplitude, the period. Which is not possible if you couldn't graph it in the first place. So you have to analyze those sine waves maybe when you're on the job. You're never going to graph them. No, worse, you're going to look at a graph and interpret it. But you're never going to graph things by hand again. Yeah, there's no point in that. It's just kind of silly. But you have to be able to do things. We're going to work with inverse trig functions and things, but we're going to do everything we need when we get to them in this class. That's the trig you need to know. So why is this important, all these identities? Well, let me give you a simple problem. This will be the last thing we do before we take a break. All right? I've got a function, and let's keep it real simple. Let's say my function is cos theta over 1 minus sine theta. There's nothing wrong with this. But I really don't like quotients of trig functions. Remember, the reciprocal of every trig function is another trig function. So for the most part, I don't like trig functions in my denominator because I might be able to manipulate them. If this were just cosine over sine, that's easy. But it's not. Darn. Quotients means I have a numerator and denominator. So I've got a quotient of trig functions. We don't like that. First thing from a calculus standpoint, products are infinitely preferable to quotients. There's no situation where a quotient is easier to work with than a product. But sums are infinitely preferable to products. Whether I have to graph or to solve or do anything. Now, I can't make anything happen. But going back to the Pythagorean identity involving sine and cosine, isn't it true that cosine squared theta equals 1 minus sine squared theta? All three of the Pythagorean identities were written as a sum of squares equaling another square. And all three could be written by moving one term as a difference of squares. All three can be written as a difference of squares, can't they? I can say tan squared equals secant squared minus 1. I can say that secant squared minus tan squared equals 1. I can do the same thing with cosine and cotangent. I can move them around to make them a difference of squares. Why do we love differences of squares in algebra? Because they're easy to factor. Isn't this true? Isn't that true? Why would I care about that? Oh, I don't know. I just happen to have a 1 minus sign over here. Any big ideas? I can play with this?
Multiply up and down by 1 plus sign.
Beautiful. Now, I don't know where this is going to get me. I know it's legal. And it's fun, just quite frankly. I mean, you guys can all go home and do this tonight, and instead of watching TV, you're going to just play with trig stuff. Okay, so my numerator is now the cosine function times 1 plus sine. That looks kind of ugly. But my denominator is now 1 minus sine squared. Why is that a good thing? Because now I can replace it with cosine squared. This up here. So now I have cos theta 1 plus sine theta over cosine squared theta. Can I cancel? You notice I did not distribute on top on purpose. Because, all right, so after all of this time, I wrote this evil quotient as this evil quotient. No. Wait, but there is definitely an improvement. I'm going to show you the single most common algebraic step I ever do. It's not even close. True or false? Left to right, no question.
I'm having trouble seeing like half the things you're writing.
Well, it's also recorded. True? Left to right, we have no question. What about right to left? Generally speaking, if you have a single term in your denominator, you're going to find it convenient to actually break up your quotient. In other words, go this way. And the way I always show this in all my classes, I always do the same thing. This, pull them apart. In my upper level classes, I don't know when this happened years ago, they always called it the butterfly technique. I guess it looks like a butterfly, I don't know. This is what I do 100% of the time when I have a quotient, where I have a single term in the denominator and more than one term in the numerator. Without exception, I do this every time. Because when I do that and I pull them apart, what do I got? I have this, which is equal to what? Oh my goosh. You started with a nasty quotient, you ended with a simple sum. Can you always do this with nasty statements? No, but it is often the case that you can, so whenever you can, you should. I tell everyone this in every calculus problem. If you can start the problem by making it easier before you start, do the algebra, manipulate it, make it simpler, and then do whatever you have to do. That original quotient is equal to this, and I guarantee you this is infinitely simpler to work with. Can you always do this? No, but you have to be able to see. Okay, so the pieces of the puzzle right there. Okay, do it first. Press the button. Okay, hopefully you had a quick break. I don't need to ever take a break. If you have those military night vision goggles, I'm the red glowing object. You see it all times a day. My motor runs like this even when I'm trying to sleep. I don't need a break. You have to have a break. You cannot sit for 2.5 hours. It's so bad for you. And what's worse is some of you are going to leave here and sit in front of a computer then for the rest of the day. You know, so the question has been asked about textbooks and about online books. I truly don't care what textbook you use. I'd prefer you not get a new textbook each semester. Okay, some instructors require a specific one, but in the last few years, most of the instructors have been pretty lenient because they know you may change classes every semester in terms of instructors, and you can't be asked to buy a new book for a 3-semester class. So most instructors will allow you to use whatever you're using. Now, if you do an online book, don't rent. It's a 3-semester class. If you rent, you're going to end up spending significantly more for a rental than you would have for a book, and you won't have it at the end of the 3 semesters. No. If you're going to do that, at least buy the ebook. I don't like ebooks personally because I don't like sitting in front of the computer any more than I have to. I already am at the computer way too much. I'd rather sit outside. I'd literally rather go to the beach with my book. Hopefully none of you take your laptops to the beach. That's a bad idea. But if you have an ebook, then you're basically chained to a computer anytime you want to do math. The other thing, it's actually a sillier thing, is I hate scrolling. I don't have the patience to scroll. You got to go through 100 pages. I'm trying to find where it just flip. Yeah, it's just so much easier for me to do it. Plus, my eyes. It's really hard for me to look at a computer for any length of time, and it's really bad for you in general. You know that. Not just your posture, but your vision, the whole blue light thing, you know, at night. So whatever you do, I'm okay with. Don't get a different book every semester. If you've had calculus before and you have the book you used last time, use that book this time. It's a source of homework questions. It's a source of practice problems. It is really hard for you to go to the internet and search for practice calculus. That's hard. You really have to have a textbook. And it doesn't matter what book, but you have to really have a source. Okay, you can't really be random. So we're going to now start the single most important concept probably in all 3 semesters of calculus, and that's the concept of limits. I remember as a calculus student, this took me so long to grasp. The algebra and everything else was trivial for me, but the concept of limit was so difficult for me to understand at first. I had a great instructor, but for some reason there was a disconnect in the explanation, and it wasn't until I started tutoring calculus a couple semesters later that I finally understood what was going on because I had to explain to somebody else. So the concept of limit is where am I headed? Not where am I getting to, but where am I headed? I may not be able to get there, but where would I be if I could? So we're going to start. And the notation we use, this is one of the rare times I actually use cursive. We write it like this. LIM as x approaches. Now, an arrow in calculus has exactly one meaning. It is not an ambiguous symbol in any context. It means approaches, never reaches. Do not use an arrow as an equal sign. I have people do that all the time. They'll say, well, my last instructor said it was okay. No. An arrow means it is not equal. So, first of all, 3 plus 4 equals 7. How do I interpret that next statement? 3 plus 4 gets really, really, really close to 7, but never gets to 7. It doesn't equal 7. It gets really close. This means it's not equal to 7. Don't use an arrow for an equal. Use an equal for an equal. Arrow means approaches, never reaches. But how close is approach? No matter how close you get, could you always get closer? Think of cutting that distance in half. I'm going to approach the wall. Okay, I'm pretty darn close. Can I get closer? Can I get closer? How close can I get? Keep going until I hit the wall? Nope, I got to stop before I hit the wall. Is there a closest point I can be, or will there always be one closer?
Always close.
No matter what I do, can I always cut the distance in half, no matter where I am?
Yes.
Yeah. There is no, but where am I headed if I could get there? The wall. My limit is the wall. I never get to the wall, but boy, do I close in on the wall. So we say the limit as x approaches a of f of x equals L. We call L will be a finite value for now. We're going to talk about infinite limits later, but not yet. That's a couple lectures down the road. So from a pictorial sense, placeholder for black inks? Oh, excuse me. This morning I ran out of ink in every single pen I used. This is a removable discontinuity at the point a comma L. Nothing weird going on here, this one's boring. In both cases, the limit as x approaches a of my function, in both cases, the limit is L. The limit is not the functional value. The limit is where am I headed if I could get there. Did I get there in this case? Yeah. Did I get there in this case? No, I removed it. It's where am I headed if I could get there. So that always confuses people. But isn't the limit the functional value? Well, often it is. It can be, but the functional value, well, I removed this point and I placed it here. So this domain is now all real numbers, isn't it? But if I was driving down this road, it's a black hole. Is the limit still L or is the limit M? Just to make it clear, f of A is equal to M. But the limit is still this. As I get closer and closer and closer and closer, where am I heading? Does that make sense? The limit in all three pictures is L. In the first case, the hole is filled in at L. Second case, I removed it, and then third case, I just simply moved it. How many have ever seen Roadrunner and Coyote? I use a lot of analogies and a lot of things. You guys don't realize how much calculus you have been exposed to in your life, but you didn't necessarily know because you might have been kids. When I prove the most important mathematical theorem probably in the history of the world, the fundamental theorem of calculus, I have to use the garbage pit scene in the first Star Wars movie where the wall's closing in. That's actually what I use to prove it. Can't prove it any other way. When I'm first developing the notion of multiple independent variables, I use the Cat in the Hat from Dr. Seuss. Thing 1 and thing 2 both represent independent variables. The cat in the hat is the dependent function. I explain everything. It's absolutely clear. You've been, all your life, you've been exposed to calculus. You did not even realize it, okay? I can't prove the quotient rule when we get to without using, Snow White and the Seven Dwarfs, because you're going to sing the song. And some of you may have learned a version of it. So we do this. Roadrunner and Coyote is the perfect example. Roadrunner and Coyote, you remember how the Coyote, he'd remove the manhole cover? You guys remember that? And so the Roadrunner would fall in? But the Roadrunner, this was brilliant, he would take the hole and he'd move the hole. Now I think a few laws of physics may have been violated in there, but no one would ever, charge him. And so when the Coyote would come around, he'd fall in the hole he created for the Roadrunner. It's crazy. He's actually doing a perfect demonstration of a removable discontinuity, and then, that's the manhole cover. He just moved it. Okay, that's the manhole cover. It sounds crazy, but the concept of limit, we try to overanalyze. We try to do too much algebra. It's just, where would I get if I could get there? So along this line on the floor, you can't see, there's a line on the floor. I'm going to remove a point. But what I'm going to do now is, I'm in 3D, I'm going to lie down on the floor and start inching towards that. In other words, I can't see the hole. Up here, I can see the hole. When I'm lying on the floor, can I see the hole as I'm moving along this line? No. So if the hole wasn't there, this is where I would get to if I could get to it. The limit is where the hole is. Now, whether the hole's filled in or not does not change the limit. That, to me, blew my mind when I was a calculus student, first of all. You mean, how did both of these have the same limit? Because I never actually have to get there. It's where am I going if I could get there. So now, let's go back to the problem we did earlier. Remember this problem we just did right before the break? I want to know what is happening to the function as x gets closer and closer to 1. Okay, just evaluate it at 1. The problem is, if I put a 1 into here, what do I get? I get 0 over 0. And here's how we write it. There is actually a formal mathematical way of writing it. 0 over 0 is not a number. It is a form. It's called an indeterminate form. There are 6 of them. We do 2 of them in this class. We do the other 4 in Calc 2. Indeterminate forms is what is the quotient taking on? What form? This is taking on the form 0 over 0. It doesn't equal 0 over 0 because that's not even a number. This means numerator and denominator are simultaneously approaching 0, which means that I can factor and cancel. I probably have a removable discontinuity. This is your favorite type of form because this is the only one that algebraically tends to be friendly. There are other indeterminate forms, particularly the exponential ones. The ones we do next semester, we do forms 0 to the 0th power, that one's crazy. 1 to the infinite power, that one's crazy. A difference where they're both approaching infinity, that one's crazy. And a product where one's approaching 0 and the other's approaching infinity. These don't have answers, you have to work them out. The 2 we do this semester are the 0 over 0, and the next week we do the infinity over infinity. And a lot of you will recognize it as something you actually did in pre-calculus. You didn't call it a limit, but you dealt with it. It's where the horizontal asymptotes of a graph come from. But that's next week. So I say, this is having this form, which means I believe I can factor and cancel. Can we factor and cancel? Yeah, we did it earlier. What does this factor and cancel as? Do you remember? Was it x plus 1? So I'm going to write x plus 1. Now, question. You're going, wait a minute. I had to write the disclaimer before. Didn't I have to write a disclaimer? I'm saying these quantities are identically equal for all real numbers, with the exception possibly of that one. I'm asking what happens as x approaches 1. X is never going to equal 1. And remember, 1 was not in the domain, but that's where I'm off the hook. X is approaching 1. It never gets there. So the limit of this quotient is equal to the limit of this statement. In other words, we can say that these quantities are identically equal for all real numbers except for 1. But I never get to 1. So now going back to the graph, this will hopefully make perfect sense. When we did this problem earlier, okay, as x gets closer and closer to 1, the y values are getting closer and closer to what? 2. As x gets closer and closer to 1, the y values are getting closer and closer to 2. Therefore, the limit is 2. Quantities approach, limits equal. I don't say the limit is approaching 2. No, the limit is 2. 2 is where I would get if I could get there. Everybody understand? This is very important that this is an equal sign. A lot of folks will say approaches, which means you're not done. Okay? But that's not even, it doesn't matter. As I got closer and closer and closer and closer, y values are, if it helps you mentally, never really do this. Pick values, if it helps you conceptually, pick values of x that are really close to 1. Okay, at 1.00000000001, then this would be 2.000000001. Got it? If x is 0.999999999, then this is 1.999. No matter how close I get to 1, that value is getting closer to 2. My limit is 2. But at that point, I can literally just take the 1 and stick it in there. That's nice. This is your favorite type of problem. This is the removable discontinuity that came from a rational function where I could factor and cancel. That's your favorite problem. That's not the only problem. That's just one problem. Excuse me. We're going to be doing things soon that involve trig functions. Those are a bit more complicated. All right. What if I have something like this? The limit as x goes to 16 of the square root of x minus 4 over x minus 16. Is this a rational function? I gotta think, what's the definition of rational function again? The answer is yes or no. It's not maybe. Is this a rational function? We love rational functions. Is it a rational function? No, because this is not a polynomial. Why is that important? Because it means I can't do the factor and cancel. Can't use synthetic division on the numerator. Oh, shoot. All the things I could do to that one, I can't do to this one. Now, if I replace an x with 16, aren't numerator and denominator both approaching 0 again? Do you all agree that this one's doing this? Even though I can't factor and cancel directly, there's a really good chance that I might be able to manipulate this. In other words, I might have to do something. Do you remember what we did with the trig quotient a little while ago? We multiplied by a conjugate and we manipulated and did stuff. The problem child here is this. The problem child cannot come from the numerator. If my denominator were not approaching 0 and my numerator was, that just means my quotient's approaching 0. 0 over non-zero, I'm pretty sure, is always 0. The problem is never the numerator, it's the denominator. So x minus 16 is the problem child. Is there a way I could get an x minus 16 on top? Is there a clever one amongst you? Come on, somebody's got to be clever. At least I only need one clever person.
Multiply by x plus 4, x minus 4.
Which is the conjugate, but not of the denominator, of the numerator. First of all, here's a really big question. Is that a legal move?
Yeah.
A lot of times we can manipulate a quotient because we multiply numerator and denominator by things. We do things all the time. In baby algebra, you had to get rid of things, so you multiply top and bottom by variable-ish things. But every now and then you've got an extraneous solution. You did something, the only way to solve the problem, or you multiplied through by a common denominator, you did all these crazy things, but sometimes it didn't work. You go, why? Because there's a couple of absolutes. You can never multiply or divide by something that can potentially equal what? 0. Because I will completely change the nature of the problem. I'm going to show you that in a moment. I can never multiply or divide by something that can potentially equal 0. I will change everything. Root x plus 4, can that ever be 0? No, it's strictly positive. In other words, is that legal? Absolutely. If I multiplied by root x minus 4, that could potentially equal 0, couldn't it? That's where I would get in trouble, but that's not what I did. I didn't need to do that. Now, in doing that, what is my new numerator? This is beautiful. X minus 16. That is a good thing. Do I want to distribute on the bottom? Oh, heck no, because then I'd have to factor again. No, don't distribute on the bottom. You already have an x minus 16. Now, one of the most common errors that people make with limits is not that they get the wrong answer, it's that they answer too soon. You didn't tell me the answer here. Why? Because numerator and denominator are both approaching 0. You told me the answer here because there's no longer a denominator. I can't give you the answer right now because both numerator and denominator are approaching 0. But if I cancel, I'm saying this quotient here is identically equal to this quotient here for all real numbers except
16.
Perhaps 16. But it's okay because I never equal 16. Why did I say except for 16? Because that's the thing we canceled. The removable discontinuity came when the root was 16. So these quantities are equal as long as x is than 16, but x isn't 16. It's only approaching 16. But this is not a problem child anymore, is it? That's a happy statement. So now as x approaches 16, what is this quotient approaching? 1 over 8. So I say the answer is 1 over 8. Isn't that cool? You like that? I mean, you gotta like that. It's kind of cool. Now, do I need a graph to explain this problem? No, because I really don't want a graph of this. This is ugly. Could I? Yeah. What I would do is, if I wouldn't do my graphing calculator, I'd just do Desmos or something and get a big picture and look at it. You don't need to. but what we have is a removable discontinuity. Whatever the graph of this looks like, this is the exact same graph with the point 16, 1/8 removed. It's literally the whole. If I asked you to graph x plus 1, there's no hole. It's just a line. But the graph of this guy has a hole right here. So we say you plucked the point and you just took it out. You removed it from the problem. That's the easiest way to remember. That's why it's called a removable discontinuity. We're going to learn there are 4 types of discontinuities. We're not going to do all of them today. This is the first one. This is our favorite one. There are a whole bunch of different ones, including, asymptotes and evil creatures like that. Okay, question? Good. Okay. When you have a question, I'd rather you ask it now than, the after class questions like, why didn't you ask it in class? Every now and then, somebody will come by my office and have the best question I've ever heard. And I'll say, can you wait till class to ask that? Why would I say that? Why would I ask you to wait till class to ask your question? Because otherwise he's the only one that got the answer when every one of you really needs to hear that question because a really good question, therefore you all get the answer. Yeah, the really good questions I'd rather ask in class because then everyone gets the benefit of the explanation. Because sometimes that really good question, you'll have it. It's not now, you'll have it later. And I'd really rather not answer it 30 separate times. Okay, so far so good? That's kind of cool. All right, now, does it always have to be numbers? Grab an example of something else. By the way, the majority of the limits that we do in this class will not be numerical. They'll be functional. Okay, here's a good one. Which one? Hold on a second. No. Well, that's kind of weird. But doesn't x have to be going to 0? Nope. Nope, x is just x. I'm having a go to 0. Okay, so if I replace a with 0, then my numerator is clearly 0. Agreed? And so is my denominator. Is this a rational function?
Yes.
That means absolutely then I can cancel what in the end? A. Because A is the thing going to 0 on bottom. I'm going to be able to cancel an A. I don't see it, by the way. I can't see it now. You're not supposed to see it now. I'm going to have to expand and manipulate. But this is my money back guarantee. You're going to be able to cancel an A before the problem's over. Again, because numerator and denominator are both going to 0 when A goes to 0. So if it helps you, I could cancel an x minus 16 because x was approaching 16. I can cancel an A minus 0 because A is approaching 0. That's why it's an A, not something else. Well, can I square this guy? I'm going to be lazy right here. X squared minus 2ax plus a squared minus x squared. Okay. Can I combine anything on top?
You can get rid of the x squared.
All right. Can I manipulate this one? Well, every term on top has an A.
You take that A out from the top.
So do I factor the A out and then cancel it? Yes, but that's 2 steps. Without skipping a step or doing a single step in your head, I want you to have the simplification in 1 step. Most of you didn't learn this. Let me show you 2 ways of doing this in 1 step. Question?
There's supposed to be 2.
Did I lose? Oh, thank you, I lost the 2. You're right. That should be what? Negative 2ax. Good catch. That will matter. There's 2 ways I can do this in 1 step. This is one that nobody ever thinks about or realizes it, but you're going to do this one later on. Do not factor it. That's one step. Then cancel it 2 steps. Multiply top and bottom by 1 over a. And what will you get? This is one way to do it. What will I get? Negative
2x plus
2x
a.
plus a over 1. I'm not going to write over 1. You can write over 1. Yes, it's correct to write over 1. I never do. The second way, here's the one thing I don't ever do. This is absolutely correct. This is what all students do. This is what all textbooks do. This is correct. Now I have to take another step to write the simplification. It's absolutely correct, but it's 2 steps. The first step was completely redundant. You know the A is going to cancel. Don't take a step to do it. Have this be the next thing you write, not the second thing you write. Do you see what I'm getting at when I said sometimes we take steps that are completely unnecessary? This is how we were all formally taught to do it. Never did it that way. It takes too long. Might make a mistake. Every time you take an extra step, you might make a mistake. Now, am I done? I haven't taken the limit yet. I think I can do this one. As a approaches 0, this is approaching. As a approaches 0,
Minus 2x.
negative 2x. So here's a case where my limit was not a number, but was a function. Just so you know, as we go on, the vast majority of limit problems that you're going to do, your limits will be functions. The vast majority. We started by doing ones that were nice and my answers were numerical, but the answer can be a function. There's nothing weird about that. Did I do the same process on this one that I did on the others? More or less? Yeah. Okay, now I'm going to show you an evil one. Sometimes the evil ones are fun. You know, you like to root for the bad guys. Everybody understands that sometimes. I mean, oh my gosh. I can't tell you how many times my oldest son, when he was really little, he'd watch the Darth Maul. It was his favorite. You know, I mean, who doesn't root for Darth Vader? I mean, he would root for the dinosaurs in Jurassic Park to eat the people when he was like 2 years old. He always roots for the bad guys. Because sometimes the evil guys are fun. But sometimes the evil ones are just, they're not fun. The next one's not fun, but it's absolutely necessary for our overall understanding. Okay? I'm going to start with a simple one. This is what is called a piecewise function. We do not spend a lot of time in calculus on piecewise functions because they're actually quite difficult to do calculus on. But they're fantastic for explaining things.
No, that's not my goal.
Yeah, it's x squared. When x is greater than or equal to 1, it's x minus 1. This is typically how you have the comma, semicolon, you have to somehow. So I've got a piecewise function. I'm defining a function in 2 pieces. Without doing any work whatsoever, what is the domain of this?
All real numbers.
All real numbers. So this ought to be easy. Except I would like to ask, what's the limit as x approaches 1 of f of x? Now, normally I wouldn't draw a picture. I'm going to draw a picture in this case, and then I'm going to do the math, because I think this will be so much easier to understand. The reason I say don't draw the picture in general is what if I made these 2 really complicated? Do you really want to spend time drawing the picture? Because we can go directly to the math without drawing a picture. But if I drew a picture of this, it's y equal x squared. So it starts here, goes through here, and like that. And then y equal x minus 1. Does that look fairly accurate? It's accurate-ish. Okay. I'm asking, what is x approaches 1? Now we have a problem here. All right. So the other day, we were kids in the elementary school together. You know, we used to go down to the train tracks. Remember that? We'd throw rocks at the train and then we'd run when they'd get mad at us and all this. So after a few years, we run into each other and we say, "Oh, do you remember when we were kids? Let's go down to the railroad track and revisit, except you live in the north part of town, I live in the south part of town, and the railroad tracks are kind of in the middle. So we plan on meeting the next day at the railroad tracks. The only problem was in the middle of the night, there was like a 8.0 earthquake. And the railroad tracks were, so you showed up at the railroad tracks, and I showed up at the railroad tracks, and I waited, and you waited, and like, oh, great, I stood up at the railroad tracks, So who was right? Or is this an impossible situation? I'm asking you, what happens as x approaches 1? This is the railroad tracks that got split because of the earthquake. This is a completely different problem than the other ones. This is where we're going to introduce the concept of one-sided limits. Okay? So the notation in this problem here, I'm going to ask you, what is the limit as x approaches 1 from the right? And this is how we indicate this. Regardless of what the number is, approaching from the right, you put a plus sign, meaning you're approaching it from numbers bigger than that number. So they have to be bigger than 1, approaching 1. Okay? The second part, I'm going to ask you to approach it from the left, which means approaching it from numbers smaller than and working your way back to the 1. Okay, you all with me on this? Now, from the right of 1, what is the function when I'm to the right of 1? This is to the right of 1. Do you agree that that's my function? My function is x squared. Can you easily evaluate this limit without doing any work? As x approaches 1, what does x squared approach?
1.
1. Okay, piece of cake. Now, I would like to approach 1 from numbers to the left of 1, which means I'm approaching along this
0.
curve, which means I'm approaching along this function. So I'm going to replace f of x with what f of x is when x is less than 1. F of x is x minus 1. And what would this limit be?
0.
Okay, Houston, we have a problem. Okay, you showed up at 1, I showed up at 0. The question is, what is this limit? We haven't addressed this. Anybody want to take a chance on this one? The worst thing, if you're wrong, I'll throw this at you, but I'm a really lousy shot. So,
It doesn't exist.
does not exist. Perfect answer. There are 3 possible answers to every limit question. The first 2 problems we did were our favorite ones. Finite. The limit is a finite number. The second one, which is also very common that we're going to explore next week, is the limit can actually be infinite. I'll give you really simple. I want y equal x squared, and I want x to get bigger and bigger and bigger and bigger. What's happening to y? It's getting bigger and bigger and bigger. Is there an upper limit? No, it's infinite. A limit can be finite, it can be infinite, or it can not exist. We say d any. We don't like d any. We think we did something wrong, but that's actually a very common answer. So the answer I'm going back to here is d any. Why is it d any is more important? So we did not address one-sided limits in either one of the problems that we did, or any of the problems we did earlier, because we didn't need to. You only look at one-sided limits if your function is changing, like a piecewise function. My function didn't change left and right of the number. Doesn't matter if I do left, right, everything's fine. But if I have a function where on the left and on the right might be different, then I have to consider one-sided. So here's something we say this way. The limit as x approaches a of f of x exists. How many are familiar with IFF? Do we know what that stands for? If and only if. That's kind of a universal shorthand. If and only if. If and only if is called a biconditional. If A, then B, if B, then A. So A, if and only if B. They're both true or they're both false, in other words. This limit exists if and only if the limit as x approaches A from the left of f of x equals the limit as x approaches A from the right of f of x. Now, I did a problem earlier where I gave you a whole and then I filled in the limits somewhere else. But the function remained the same on both sides. I didn't need to do one-sided limits in that case. But I do in this case because the function on the right and the function on the left are completely different functions. Let me change this. Change that to any real number other than 1. Make it -3. Make it +5. Would I have any issues in this problem if that number wasn't a 1? Would it be an easy problem if it wasn't a 1? Yeah, because I'd just be right on the graph. But because I chose the place where I changed the definition, right, from one function to the other, that's where it might be iffy. How can I make it so the function exists, or so the limit exists? What if I made this x squared -1? What would that do? Would that move this piece down? Would that make the limit exist? Yes. Would I still have to do one-sided limits? Yeah, because I have 2 different functions. So in a piecewise function, you always do one-sided limits in this case. Now, here's one of the nice things. This limit did not exist, but both of the one-sided limits did. So for the most part, one-sided limits generally exist. Generally exist. There is an exception. This is one of my favorite exceptions because it stumps everybody. What is the limit as x approaches 0 of the square root function? Well, that's easy. That's easy, isn't it? It's the last thing we're going to do today. Obviously, the answer is what? I'm winking at you with my
Should
left
be
eye.
0.
You know something's up when it's the left eye wink every time. The answer is obviously what?
Does not exist.
Does not exist. Good. What? Why is it a D and E? Because there's nothing to the left. The limit from the right is 0. The limit from the left does not exist because I'm outside the domain. That's why I said this one is tricky. This stumps everybody, but after the fact you go, oh, perfect sense. Because the domain of this is 0 to infinity. There's nothing to the left. So what if I change this to a plus sign here? Now what's the limit? 0. Good. That one should be easy. But the overall limit not existing would stump us because we weren't expecting that. All right? Can you go ahead and press the red button? We'll stop the recording.